Part 1. The Close Encounter No One Will Be Ready For. While the world fixated on 3I Atlas, that mysterious interstellar drifter gliding through the solar system like a cosmic phantom, something far more immediate would be heading our way. Something humanity had known about for decades, something capable of reshaping global history in a single afternoon in 2029. Its name would be 99942 Apophis, better known by its ominous title, the God of Chaos. Fitting, isn't it? Named after the ancient Egyptian deity of darkness and destruction, this roughly 1,115-foot asteroid would sweep past Earth on April 13, 2029, diving low enough to slip beneath some of our satellites. It would pass just 19,000 to 20,000 miles above the planet's surface, closer than the geostationary belt where GPS signals and television broadcasts originated. For comparison, the International Space Station orbited about 250 miles up. Apophis would be 75 times farther out than that, yet absurdly, breathtakingly close for something of its size. To grasp the scale, an asteroid this large passing so near Earth would be essentially unprecedented in recorded human history. Smaller objects had passed closer, certainly, but nothing around 1,000 feet wide, massive enough to unleash the energy of hundreds of nuclear weapons, had ever skimmed our satellite infrastructure. It would be a once-in-a-millennium event, happening squarely within our lifetime. Picture its trajectory. Imagine Earth as a blue marble floating in space, wrapped in rings of satellites. The innermost ring holds craft in low orbit. Above it sits medium orbit with navigation satellites, and beyond that the crowded geostationary highway of communications satellites hovering above the equator. Apophis would thread the needle between Earth's atmosphere and that geostationary ring. It would be visible to the naked eye in several regions of the world, a bright, fast-moving point shifting noticeably against the starry backdrop. Crowds would fill the streets, children would point, someone would stream it live. It would dominate the news cycle for a day, maybe two, and then fade as people assumed the danger had safely passed. But this was the part that would keep planetary scientists awake at night. The question NASA and the European Space Agency would address carefully, diplomatically, in public statements. What if that flyby didn't simply give us a spectacular sky show? What if it fundamentally changed Apophis itself? What if Earth's gravity didn't merely tug the asteroid along its path, but reshaped it, altered its rotation, disturbed its surface, triggered internal stresses no model had fully captured? And what if those subtle, invisible changes nudged Apophis onto a trajectory that would bring it back? The official stance sounded reassuring. NASA had stated clearly that Apophis posed no impact risk in 2029 or in the following century. The European Space Agency echoed this. The calculations had been checked and rechecked. Orbital models were solid. Everything looked safe. But below that competent exterior lived a more tangled truth. Orbital dynamicists, scientists who specialized in computing asteroid trajectories, were still publishing studies on Apophis, still modeling faint accelerations, still mapping uncertainty regions, still asking what if about forces measured in millimeters per second. Why would they do that if the case were truly closed? Because they understood something the public had not yet fully absorbed. The 2029 flyby would not be the end of the story. It would be the beginning. It would be the moment tiny uncertainties could snowball into catastrophic ones. The moment our current safety margin could evaporate. Think of it this way. At present, Apophis followed a predictable orbit. Radar had tracked it. Observatories had recorded its position against background stars. Models projected its path years and decades ahead, but every model, no matter how precise, rested on assumptions. Assumptions about mass, reflectivity, spin rate, thermal properties, unseen external forces. What would happen when some of those assumptions proved wrong? What would happen when the 2029 encounter introduced variables we had never accounted for? What would happen when the asteroid emerging from that flyby was not the same asteroid that went in? The answer was simple and unsettling. Our carefully built probability maps, our comforting century-scale safety estimates, could become obsolete overnight. A completely different threat profile might emerge, and we might not recognize it immediately. The changes could be so subtle that months or even years of follow-up observations would be needed before scientists realized the models had quietly collapsed. This wasn't dramatization. It was what cutting-edge research truly implied if one read between the lines. Papers were already exploring scenarios where Apophis would undergo tidal reshaping during the approach, where its rotational state would shift, where surface material would migrate and alter the rock's thermal behavior. Each scenario opened the door to orbital changes not yet fully mapped. So while the world watched the distant interstellar visitor that posed no real danger, the real story would unfold far closer to home. The god of chaos would approach, and when it came, humanity would have to hope its understanding of the asteroid was as complete as it believed. Because if not, April 13, 2029 would not be remembered as the day we dodged a bullet. It would be remembered as the day we sealed our fate without even realizing it. Part 2. The comfortable lie we all believe. Let's talk about what NASA actually stated. Not the headlines, not what someone's uncle posted online, but the precise language used by the agency that tracks near-Earth objects professionally. In March 2021, the European Space Agency formally removed Apophis from its risk list. NASA followed with matching statements. The line the world clung to was simple and soothing. Apophis would pose no impact risk for at least the next century. The Planetary Society, one of the most respected space advocacy organizations on Earth, confirmed this repeatedly. Case closed. Time for the internet to stop worrying about 2029 or 2036. We were safe. Except that wasn't the whole picture. Those statements were technically correct based on current data and current models, but they carried invisible footnotes. Footnotes about confidence intervals, measurement uncertainties, physical processes still under study, and the enormous difference between no measurable risk with today's instruments and no possible risk under all circumstances. Here was the uncomfortable truth. Every time an asteroid makes a close pass by Earth, its orbit changes. It must change. Basic physics. Earth's gravity tugs on it, alters its speed, shifts its trajectory. When an object passes millions of miles away, that shift is tiny, irrelevant, barely worth noting. But Apophis wouldn't pass millions of miles away. It would pass 19,000 miles out. At that distance, Earth's gravity wouldn't be a minor influence. It would be the dominant force acting on the asteroid for several critical hours. Scientists had modeled this, of course. They had run simulations predicting how Apophis's orbit would shift after the 2029 flyby. They had calculated where it would be in 2036, when it would return for a far more distant encounter. They had mapped later approaches decades beyond that, and in all those models, based on everything known now, Apophis remained harmless. No impact, comfortable margins. But those models relied on knowing exactly how Apophis would respond to Earth's tidal forces in 2029. And here was the twist. We didn't know exactly. We couldn't know until the event happened. When you talk about tidal forces, You're describing how Earth's gravity pulls different parts of the asteroid with different strength. The near side feels a stronger tug than the far side. That difference creates internal stress. If the asteroid were a solid, cohesive block, a single fused mass, those stresses might not matter. The rock would hold. But what if Apophis wasn't solid? What if it was a rubble pile? A loose collection of boulders and gravel held together only by weak gravity and a bit of friction. Many asteroids turned out to be exactly that when explored up close. If Apophis belonged to that category, the tidal forces could reshape it. Rocks could shift, mass could redistribute. Its structure could deform. And if the shape changed, if the distribution of mass shifted, then Apophis's interaction with sunlight would change. The way it heated and cooled would change. Its rotation would change. Every one of those factors fed directly into orbital calculations. Suddenly, the reassuring long-term predictions would require recalculation. And maybe, just maybe, those recalculations would tell a different story. This wasn't wild speculation. It was grounded in real physics and real missions. In 2019, Japan's Hayabusa 2 landed on asteroid Ryugu and found exactly this rubble pile structure. NASA's OSIRIS-REx visited Bennu and discovered a surface so loose and unstable that when the spacecraft attempted to collect a sample, it sank into the ground with almost no resistance. We knew asteroids could be surprisingly fragile, surprisingly porous, surprisingly sensitive to forces that would seem insignificant. And we knew Apophis would pass through a gravitational environment that was anything but insignificant. That combination alone deserved caution before anyone declared the situation fully resolved. Then came another complication, the Yarkovsky effect. The short version: asteroids absorb sunlight, warm up, and then radiate heat into space. That thermal radiation produces a tiny thrust, a microscopic rocket engine. Over decades and centuries, that thrust can shift an asteroid's orbit significantly. For Apophis, scientists had been measuring the Yarkovsky effect. They had tracked how that thermal push slowly altered its orbit. They had already included this push in their models. But here was the catch. The Yarkovsky effect depended entirely on the asteroid's thermal properties, how it absorbed heat, reflected light, and radiated energy. If the 2029 flyby changed the surface, if tidal forces rearranged rocks, exposed new patches, buried others, then its thermal behavior would change. And if the thermal behavior changed, the Yarkovsky effect would change, perhaps only by inches per day. Let's stretch that over the 20 years leading up to the 2051 encounter, and those inches became hundreds of yards of uncertainty. Hundreds of yards mattered. They mattered a lot when predicting a possible impact trajectory. So what were scientists truly saying when they declared we were safe for a century? They were saying that, based on current assumptions, current models, and current measurements, Apophis posed no threat. And that was likely accurate. The odds strongly favored safety. But they were also saying, quietly, between the lines, that those assumptions needed real-world validation. The models needed testing against actual data from the 2029 encounter. The work wasn't finished. Observation had to continue. That was why the European Space Agency planned the Ramses mission. That was why NASA redirected OSIRIS-APEX toward Apophis. Not because disaster was expected, but because uncertainty was respected. Because probably safe was not the same as absolutely safe. Because April 13th, 2029 would be humanity's best and possibly only chance to turn assumptions into knowledge. Part 3. The invisible forces that could change everything. Let's examine what will actually happen when Apophis plunges through Earth's gravitational well on April 13th, 2029. Not the simplified version repeated in headlines, but the real physics that keeps astrophysicists awake at night, running simulations over and over. As Apophis approaches, it won't feel Earth's gravity as a single uniform pull. It will experience tidal forces, the same kind of forces the Moon exerts on Earth's oceans, raising and lowering tides twice a day. But for Apophis, these forces will be far more intense because it will pass much closer, and because it is a solid body rather than a shifting sea of water. Imagine holding a rubber rod and pulling one end harder than the other. The rod stretches, bends, warps. That is essentially what Earth's gravity will do to Apophis. The side facing Earth will feel a stronger tug than the far side. That imbalance will generate stress throughout the asteroid's entire structure. If Apophis is a coherent monolith, a single block of cooled, hardened rock, it might hold together without much trouble. Rock is strong. Rock can resist sizable stress without failing. But if Apophis is a rubble pile, a cluster of smaller boulders held together only by weak gravity and the friction of contact, things get more complicated. Radar observations from the Arecibo Observatory before its collapse in 2020, along with later measurements from other facilities, suggest that Apophis is likely moderately cohesive. Not just a random heap of debris, but moderately cohesive is not the same as perfectly solid. It could still contain internal fractures, weaker layers, regions where stones cling together loosely. And here is the crucial point. We will not know the truth until Apophis completes its 2029 encounter, and we see the consequences. Tidal forces might shake the asteroid, causing internal rocks to shift. They might generate new fractures or widen older ones. They might trigger minor landslides on the surface as loose material slips and resettles. Each of those changes would alter the asteroid's internal mass distribution. And when the mass distribution changes, the moment of inertia changes, the rotational equivalent of mass. That shift would affect how Apophis spins. Its rotation could speed up. It could slow down. Its axis could wobble or drift into a new orientation. Rotational changes matter because they directly influence the Yarkovsky effect, that subtle thermal push created by uneven heating and cooling. As an asteroid rotates, different areas heat under sunlight, then cool in shadow, radiating heat into space. That emission carries momentum, generating a tiny but continuous thrust in the direction of the outgoing thermal radiation. The strength of the Yarkovsky effect depends on rotation speed, the tilt of the rotation axis, and the asteroid's thermal properties. Change any of those, and the thermal thrust changes. Change the thrust, and the long-term orbit shifts. To understand how sensitive this is, over the last 20 years of tracking Apophis, scientists have measured the Yarkovsky effect shifting its orbit by roughly 560 feet per year. That doesn't sound like much, but in 20 years, that becomes more than 2 miles. In 50 years, more than 5 miles. And when predicting whether an asteroid might strike a planet with a diameter of about 7,900 miles, those miles of uncertainty matter enormously. Now consider what happens if the 2029 flyby changes the Yarkovsky effect by just 10%. Maybe the rotation speeds up slightly. Maybe a dust layer shifts, exposing rock with different thermal behavior. That tiny 10% change would become an extra 56 feet of orbital drift per year. Over 20 years, that adds up to more than 1,100 feet, a difference our current models do not include. Here is what truly unsettles orbital dynamicists. There exists a narrow region of space called a gravitational keyhole. It is only a few hundred feet across. If Apophis passes through that narrow corridor in 2029, Earth's gravity will bend its orbit so precisely that it would return exactly 7 years later, on April 13, 2036. on an impact trajectory. Based on present observations, the odds that Apophis will pass through that keyhole are extremely low. NASA estimates the probability at less than 1 in several million. ESA agrees. Radar data and optical tracking all indicate a safe passage. The 2036 scenario is no longer considered a realistic threat. But here is the catch. Those probability calculations assume we know exactly where Apophis will be at its closest approach in 2029. They assume our Yarkovsky models are correct. They assume no unmodeled forces act on the asteroid. What if one assumption is slightly off? What if Apophis vents a minuscule amount of gas, something never detected from Earth? What if the internal structure isn't what we think, making tidal force predictions slightly wrong? What if the 2029 encounter itself triggers unseen changes that alter the trajectory? Then, the 1 in several million odds may no longer apply. They could grow. They could become 1 in 100,000, 1 in 10,000. Still small, but no longer trivial when discussing a potential planetary impact. This is why scientists continue studying Apophis, why observation campaigns remain active, why 2 separate spacecraft missions will investigate Apophis closely during the 2029 pass, not because disaster is expected, but because the gulf between highly unlikely and impossible must be respected. Another rarely mentioned factor deserves attention. We do not know Apophis's internal composition in detail. We know it is roughly 1,115 feet across. We know it completes an orbit around the Sun every 323 days. We know it rotates once every 30.6 hours. We know its density is probably typical for rocky asteroids, around 3.2 grams per cubic centimeter. But we do not know whether it contains internal voids. We do not know whether weaker layers or pockets of porous material exist. We do not know the geometry of its inner structure. And all those structural details matter when predicting how an asteroid responds to severe tidal forces. This is why Ramses and OSIRIS-APEX are so crucial. These missions will not merely capture beautiful photos. They will measure how Apophis vibrates after the encounter. They will map shifts in its shape. They will detect any dust plumes or debris clouds released during the passage. They will measure its gravitational field to infer mass distribution. They will track changes in rotation. Every one of these measurements will feed directly into refined models of future encounters. They will turn assumptions into knowledge. They will reduce uncertainties. And potentially, though we hope not, they may show that Apophis's 2036 return and later flybys warrant far more attention than currently assumed. Part 4. The Yarkovsky Effect, the invisible push that alters destinies. Now let's examine the Yarkovsky effect in full detail, because this seemingly insignificant force could be the thin line between safety and catastrophe. Imagine you are an asteroid drifting through space. Sunlight pours over you. Your dayside heats up as it absorbs solar energy. Then you rotate, and that warm side turns into darkness. In shadow, it cools, releasing its stored heat back into space as infrared radiation. Here is the crucial part. When that heat radiates outward, it leaves as photons. Photons have no mass, yet they carry momentum. When billions upon billions of them shoot away from your surface in one direction, they push you ever so slightly in the opposite direction. It is a microscopic rocket engine, powered not by fuel, but by temperature. For an object the size of Apophis, this push is unbelievably small. A force measured in fractions of a Newton, the weight of a few coins on Earth. But that force acts constantly, 24 hours a day, 365 days a year, for decades and centuries. And, in the frictionless vacuum of space, even tiny forces accumulate into enormous effects over enough time. Scientists identified the Yarkovsky effect more than a century ago, but only in recent decades have we been able to measure it precisely in real asteroids. For Apophis, measurements began in earnest after its discovery in 2004. Over the last 20 years, astronomers have tracked its position against distant stars with exquisite detail, measuring how its orbit deviates from what pure gravity predicts, and they found the deviation. A small, consistent drift caused by the Yarkovsky effect, pushing Apophis roughly 560 feet per year along its orbit. That confirmed the effect was real and active for this specific asteroid. It also meant that any long-term prediction of Apophis's path had to include this thermal push. Current orbital models include it. They factor in the measured Yarkovsky effect to determine that Apophis will remain safe for the next century. But here comes the problem. These models assume the Yarkovsky effect will remain constant. They assume the asteroid's thermal properties will not change. They assume its rotation will stay stable. What happens if the 2029 encounter breaks those assumptions? Think of it this way. The Yarkovsky effect depends on several variables. Rotation speed matters because it determines how long each region remains under sunlight before moving into shadow. Faster spin means less heating time, less accumulated warmth, and a weaker Yarkovsky push. Slower spin means the opposite. Surface properties matter as well. A dark, dusty asteroid absorbs far more sunlight and heats up more than a bright, reflective one. An asteroid with high thermal conductivity will distribute heat more evenly across its interior. One with low conductivity develops sharp temperature gradients between day and night, strengthening the Yarkovsky effect. Even shape matters. Craters, ridges, boulders, and irregular folds create pockets of shadow and regions that trap or re-radiate heat in complex ways, altering the thermal pattern. Now imagine what Earth's tidal forces could do to these variables during the 2029 passage. If tidal stress shakes loose surface dust and exposes fresh rock beneath, the thermal properties change. If internal stones shift, the mass distribution changes, affecting the moment of inertia and rotation rate. If small landslides reshape surface features, the heating and cooling pattern changes. Any of these effects would alter the Yarkovsky thrust, and because that thrust acts continuously for years and decades, even a small alteration can accumulate into a substantial shift in where the asteroid will be far into the future. Here's a tangible example. Suppose the 2029 encounter speeds up Apophis's rotation by just 5%. A subtle change that might be difficult to detect immediately from Earth. That 5% faster spin could weaken the Yarkovsky effect by about 26 feet per year. That doesn't sound dramatic, but by 2036, 7 years later, it becomes 182 feet of orbital shift. By 2051, 572 feet. By 2068, 1,014 feet, and the gravitational keyhole that could put Apophis on a collision course is only a few hundred feet wide. Now imagine the opposite scenario. The flyby slows Apophis down slightly. If tidal forces impose even a faint drag, shaving off only a small percentage of its rotational speed, the Yarkovsky effect strengthens. Apophis would drift farther along its orbit than current models predict. The problem is simple. We don't know which scenario will occur, or whether any change will occur at all. Models suggest rotational changes will be tiny, perhaps under 1%, maybe fractions of a percent, but likely is not certain, and when evaluating risks that involve entire cities, the difference matters. This is exactly why both planned space missions, Ramses and OSIRIS-APEX, will carry instruments designed to measure Apophis's rotation with extreme precision before, during, and after the 2029 encounter. They will measure the asteroid's orientation against background stars. They will track how surface landmarks move as it spins. They will detect even the most minuscule changes in its rotation period. These measurements will feed directly into refined Yarkovsky models, reducing uncertainties from hundreds of feet to perhaps a few dozen. Greater precision means stronger predictions for where Apophis will be in 2036, 2051, 2068, and beyond. But there is another twist. The Yarkovsky effect is not the only non-gravitational force acting on Apophis. There is also the Yorp effect, the Yarkovsky-O'Keefe-Radzevsky-Paddock effect, which can gradually change an asteroid's rotation rate over time. It is caused by the same absorbed and radiated heat, but produces torque rather than linear thrust. For most asteroids, Yorp is incredibly weak, requiring thousands or millions of years to create noticeable change. But for some asteroids with unusual shapes or spin histories, it can be more significant. And we do not yet know how strong the Yorp effect is for Apophis, because we have not observed it long enough to measure it directly. If Yorp has been slowly shifting Apophis's rotation over the last 20 years, ever so slightly, then our Yarkovsky models might be off by a few percent. Not catastrophically off, but enough to matter when predictions extend decades into the future. And then comes another possibility: outgassing. Some asteroids contain volatile ices trapped in cracks or pores. When heated by sunlight or mechanical stress, these ices can sublimate into gas and escape into space, producing a small but real thrust. For Apophis, significant ice seems unlikely. Its orbit brings it too close to the Sun for long-term survival of volatiles. But unlikely is not impossible. If tidal forces in 2029 open new fractures, exposing tiny pockets of water ice or CO2 ice that survived in insulated cavities, a brief outgassing event could occur. The thrust would be small, but enough to alter the orbit in unpredictable ways. Again, a low probability scenario. But low probability does not mean irrelevant when considering potential asteroid impacts. That is why Ramses and Osiris Apex will also watch for any comet-like activity, dust, gas, debris around Apophis. The central point is simple: the Yarkovsky effect. This subtle force born from nothing more than sunlight and heat is simultaneously one of the best understood and most uncertain aspects of Apophis's orbital evolution. We have measured it, modeled it, built predictions with it. But until we observe how Apophis reacts to the intense stresses of its 2029 encounter, we will not know whether those models remain valid. And if they do not remain valid, if the encounter alters the Yarkovsky effect in unforeseen ways, then the comfortable century of guaranteed safety may shrink dramatically. Part 5. Impact Scenarios. What is truly at stake? Let's confront what would actually happen if, against all current odds, Apophis ended up on a collision trajectory with Earth. Not to provoke panic, but because understanding the consequences explains why scientists treat even low probabilities with such gravity. An asteroid roughly 1,115 feet wide, striking Earth at cosmic velocity, about 7.8 miles per second, would unleash energy equivalent to 1,000 to 1,500 megatons of TNT. For comparison, the most powerful nuclear device ever detonated, the Soviet Tsar Bomba in 1961, released about 50 megatons. An Apophis impact would be 20 to 30 times more energetic. But here is the essential point. Unlike nuclear weapons, which release much of their energy as thermal radiation and atmospheric blast, an asteroid impact deposits its energy in drastically different ways, depending on where it strikes. And that changes everything. If Apophis struck the ocean, as statistics suggest is most likely, considering oceans cover 71% of Earth's surface, the impact energy would convert mainly into a massive tsunami. Models show initial waves reaching 100 to 165 feet near the impact zone, weakening as they spread but still potentially devastating hundreds of miles away. An Atlantic Ocean impact, for example, could send destructive waves toward North America, South America, Europe, and Africa. Coastal cities with little warning time could face catastrophic flooding. Casualties would depend heavily on available warning, whether there were hours to evacuate or only minutes. If Apophis hit land, the picture changes completely. The impact would excavate a crater about 2 to 2.5 miles across. Everything within 6 miles of ground zero would be instantly annihilated. Within 30 miles, buildings would collapse, fires would ignite, and thermal radiation would scorch exposed materials. Farther out, within 60 to 120 miles, the region would endure devastating winds, falling debris, and impact-triggered earthquakes. Seismic waves would register around the world, resembling a magnitude 7 or 8 earthquake. A major city suffering a direct hit would vanish completely. Millions would die instantly. Tens of millions would be injured. Infrastructure would collapse across a region the size of a small country. But here is the part many discussions overlook. Even a remote land impact would have global consequences. Dust and debris blasted into the stratosphere would circulate around the planet, dimming sunlight for months. Temperatures would drop. Growing seasons would shorten. Food production would decline. This would not be a dinosaur-level extinction event. Apophis is far too small for that. Human civilization would endure, but the economic shocks, humanitarian crises, and geopolitical instability could last for years, perhaps decades. That is why even a 1 in 10,000 probability is not something you shrug off. When the potential consequences are so catastrophic, even very low odds demand serious attention. And here comes the unsettling twist. With enough warning, humanity could probably prevent the impact. Asteroid deflection technology has advanced dramatically. NASA's DART mission in 2022 proved that we can alter an asteroid's orbit by slamming a spacecraft into it. DART changed Dimorphos's orbital period by about 33 minutes, far more than the minimum needed to classify the mission as a success. That experiment proved kinetic impactors work. With enough lead time, years or decades, we could launch one or several spacecraft to nudge Apophis just enough to miss Earth. The required change would be tiny, altering the asteroid's speed by only fractions of an inch per second could translate into thousands of miles of orbital shift over many years. But here is the problem. Lead time is everything. If we discovered that Apophis was on a collision course only months before impact, options would become severely limited. There would be no time for a carefully planned deflection mission. We would be left with desperate last-minute attempts with no guarantee of success. This is precisely why the 2029 flyby is so crucial. That encounter will be our best chance to reduce uncertainties, to turn probabilistic estimates into reliable knowledge about Apophis's long-term path. If a threat ever emerges, 2029 is when we will find out, and that knowledge would give us decades, not months, to react. Now let me be precise. Based on all current data, current models, and current calculations, Apophis will not hit Earth. Not in 2029, not in 2036, not in any predicted encounter for at least the next century. The odds overwhelmingly favor safety, but overwhelmingly likely is not the same as absolutely guaranteed. And the space between those two concepts is where responsible planetary science lives. It is where researchers refine measurements, improve models, plan missions, and ask hard hypotheticals. Because if decades of asteroid exploration have taught us anything, it is that asteroids surprise us. Ryugu turned out more porous than expected. Bennu, far looser and more fragile than predicted. Each time we visit a new asteroid, we discover our assumptions needed adjustment. Apophis will be another learning opportunity. The 2029 flyby will reveal things we do not currently know. It may confirm our models. It may surprise us. It may show that physical processes we only partially understood play larger roles than expected. Either way, we will be better informed. And better informed means better prepared. Better prepared to track other hazardous asteroids. Better prepared to plan deflection missions when needed. Better prepared to protect civilization from one of the few natural disasters we can actually prevent, if we see it coming early enough. That is the real stakes here. This isn't just about Apophis, though Apophis is important. It is about strengthening the infrastructure, expertise, observational systems, modeling capabilities, and mission technologies that allow us to defend Earth from the entire population of near-Earth objects. Hundreds of thousands of asteroids out there are large enough to cause immense destruction. We have cataloged perhaps 95% of the largest ones, objects over a kilometer in size, that could cause global effects. But we are far less complete for asteroids the size of Apophis. Many remain undiscovered. Each newly discovered asteroid must be tracked. Each orbit must be modeled. Each potentially hazardous object must be monitored for years to ensure it poses no threat. It is endless work, but indispensable. And Apophis, because of its size, its orbit, and its close 2029 encounter, has become a test case, a chance to evaluate our entire planetary defense system under controlled conditions, where the stakes are high enough to matter, but not so high that we expect disaster. If we do this correctly, if we characterize Apophis thoroughly, before, during, and after its encounter, if we can predict its future orbit with real precision, if we can demonstrate that our planetary defense toolkit works, then we gain confidence that we can handle the next threat. And there will be a next threat. Maybe not from Apophis, maybe not soon, but someday in some future decade, another asteroid will be discovered on a dangerous trajectory. And when that moment arrives, everything we learn from Apophis, every model, every technique, every technological capability will shape how we respond. Part 6. The missions that will give us answers. Now let's examine how we will obtain the answers we need. Because this time, instead of watching Apophis passively from Earth, spacecraft will go out to meet it. 2 independent missions, one European, one American, will be positioned to witness the 2029 encounter directly. First comes Ramses, the rapid Apophis mission for space exploration, developed by the European Space Agency. ESA has been designing this mission specifically for the 2029 flyby. The plan is to launch Ramses in 2028, giving it enough time to rendezvous with Apophis before the close approach. Ramses will reach the asteroid weeks before April 13, 2029. During that time, it will map Apophis's surface meticulously. Every ridge, every boulder, every small crater. It will measure the asteroid's shape precisely, determine its rotation, and characterize its thermal properties. Then, as Apophis plunges through Earth's gravitational well, Ramses will watch in real time. It will record how tidal forces affect the asteroid. It will detect changes in rotation. It will observe whether dust or debris is released. It will measure how the asteroid's shape distorts under stress. And after the flyby, Ramses will remain with Apophis, documenting how the asteroid settles into its new orbit. It will repeat measurements of shape, rotation, and thermal behavior, comparing them to pre-flyby data to quantify exactly what changed. This information will be invaluable. Instead of guessing what happened based on telescopic observations, we will have a direct witness, a spacecraft on site documenting everything. But Ramses will not be alone. NASA will send its own mission, one with an unusually interesting history. The spacecraft OSIRIS-APEX was originally built as a backup for OSIRIS-REx, which visited the asteroid Bennu and returned a sample to Earth in 2023. After delivering its sample, OSIRIS-REx still had fuel and functioning systems. So NASA did what efficient space agencies do. It reused the spacecraft. It was renamed OSIRIS-APEX, the Apophis Explorer, and redirected toward Apophis. OSIRIS-APEX will arrive in April 2029, just in time for the flyby. Like Ramses, it will observe Apophis before, during, and after the encounter. But OSIRIS-APEX has a unique capability. It can fire its thrusters directly into the asteroid's surface, kicking up dust and exposing fresh material. OSIRIS-REx used this technique successfully on Bennu. By disturbing the upper layer, OSIRIS-APEX will reveal what lies beneath the top layer of dust and regolith. This matters because surface properties directly affect the Yarkovsky effect. Understanding Apophis's surface composition and structure will improve predictions of how it absorbs and radiates heat, and thus how its orbit will evolve. But here's the critical part. These missions are planned, designed, but not yet fully approved and funded. Ramses still requires final approval from ESA member states. OSIRIS-APEX has its spacecraft ready, but NASA must secure continued funding for extended operations. This means the years 2025 and 2026 are critical. These missions could be fully approved and funded, or delayed or canceled due to budget constraints. If that happens, humanity will lose its chance to observe the 2029 flyby up close. Consider what that would mean. This is a once-in-a-millennium event, an asteroid roughly 1,115 feet wide, passing within the geostationary satellite belt. Our one opportunity in a lifetime to see how an asteroid of this size responds to extreme tidal forces. Without spacecraft present, we would rely solely on Earth-based observations, limited by atmosphere, weather, angle, and resolution. Ground-based data will still be collected. Every major observatory will track Apophis. Radar systems will scan it. Telescopes will image it. Spectrographs will analyze its reflected light. But none of it compares to spacecraft observations. The difference between ground-based data and up-close spacecraft data is the difference between viewing your house from a satellite versus standing inside it. Both provide information, but the clarity and certainty are entirely different. So when you hear about Ramses and OSIRIS-APEX in the news over the next years, mission approvals, budget votes, design milestones, pay attention. Decisions made in conference rooms across Europe and North America will determine how well we understand Apophis after 2029. And that understanding directly translates into safety. Better data leads to better models. Better models lead to more accurate predictions. Accurate predictions tell us definitively whether Apophis poses any threat in future encounters, or whether we can dismiss the danger forever. But these missions do more than study Apophis. They serve as proving grounds for planetary defense techniques. Every instrument developed, every measurement method refined, every operational protocol tested becomes part of our long-term toolkit for dealing with future hazardous asteroids. For example, Ramses will use advanced navigation cameras to track its position relative to Apophis, an improved version of systems that could guide future deflection missions. Both spacecraft will measure Apophis's gravitational field, helping validate methods for estimating asteroid mass, which is essential for calculating how much force is needed to alter its path. Even the operations themselves matter. Flying a spacecraft alongside a fast-moving asteroid, close enough to collect data, far enough to avoid danger, demands precision navigation and autonomous control software. That operational experience will flow directly into future missions. There is another reason these missions matter: public engagement. On April 13, 2029, millions of people worldwide will watch Apophis pass by. It will be visible to the naked eye across parts of Europe, Africa, and Asia. Social media will explode. News broadcasts will follow it. In that moment, having real spacecraft at Apophis sending live images will transform the event from a distant astronomical curiosity into a vivid collective experience. People will see the asteroid close up. They will see Earth from Apophis's perspective. They will watch science unfold in real time. That kind of public engagement builds support for space science and planetary defense. When people see taxpayer money producing real missions with real results, they are more likely to support sustained funding. And sustained funding is essential. Planetary defense is not a one-time project. It is an ongoing commitment requiring nightly telescope observations, continual data analysis, mission planning, and decades of operations. It only works if maintained continuously. So what needs to happen for Ramses and Osiris Apex to fly? For Ramses, ESA must approve and fund the mission, likely in 2025. That requires European governments to agree, and scientists to communicate clearly why the mission is necessary, why now, and why no future asteroid will offer as good an opportunity. For Osiris Apex, NASA must commit funding for years of extended operations, mission control staffing, data processing, deep space network communication time. These funds must appear in NASA's yearly budgets and survive congressional approval. None of this is guaranteed. Both missions depend on decisions made soon, decisions that prioritize planetary defense over other competing demands. If you care about planetary defense, if you believe understanding Apophis matters, then the time to pay attention is now. The debates about mission funding and scientific priorities happening in 2025 and 2026 will determine whether we seize the opportunity offered by the 2029 flyby, because we will not get another chance like this. The next Apophis flyby, in 2036, will be far more distant, too distant for detailed observation. Later encounters will be even less favorable. April 13, 2029 is the one moment when we can observe this phenomenon up close. We should not miss it by staying home when we could be right there. Part 7. Planetary Defense, Beyond Just Watching. Let's imagine the worst-case scenario. Suppose the 2029 observations reveal that, against all present expectations, Apophis ends up on a trajectory that will put it on a collision course with Earth during a future encounter. Maybe in 2036, maybe in 2051, maybe later. What would we actually do? The good news is that, unlike almost any other natural disaster, asteroid impacts are preventable if they are detected early enough. We cannot stop earthquakes. We cannot steer hurricanes. We cannot shut down volcanoes. But with technology that already exists, we can change an asteroid's orbit. The most dramatic demonstration came on September 26, 2022, when NASA's DART spacecraft deliberately slammed into a small asteroid called Dimorphos at roughly 4.1 miles per second. The impact was spectacular, producing a huge plume of debris captured on video by DART in its final seconds and by a small Italian CubeSat flying nearby. The outcome exceeded expectations. The impact changed Dimorphos's orbital period by about 33 minutes, far more than the minimum 73 seconds required to declare the mission successful. That large shift happened partly because Dimorphos turned out to be a fairly loose rubble pile, and the impact ejected a great deal of material, creating a powerful recoil that amplified the orbital change. DART proved that kinetic deflection works. If we have enough warning, years, preferably decades, we can change an asteroid's orbit enough to turn a hit into a miss. No Hollywood-style nuclear explosions are required, although nuclear options remain on the table for extreme scenarios. All that's needed is a well-aimed impactor, moving fast enough. For Apophis specifically, calculations suggest that an impactor roughly comparable to DART, launched with sufficient lead time, could deliver the needed push. The exact amount of deflection depends on when the mission launches. The earlier we act, the less force is required, because small changes in speed accumulate into enormous changes in position over long timescales. Picture this. In 2030, imagine we learned that Apophis would strike Earth in 2051. That would give us 21 years. A deflection mission launched in 2035 or 2036 would need to change Apophis's speed by only a tiny amount, on the order of fractions of an inch per second. Over 15 years, that slight nudge would translate into tens of thousands of miles of orbital displacement, easily enough to miss Earth completely, but timing is everything. If we waited until 2045, with only 6 years left, we would need a much larger change in velocity, demanding a bigger impactor or multiple missions. And if we did not recognize the danger until 2050, with just a year to go, our options would shrink to a short list of risky, last-ditch attempts. This is exactly why the 2029 flyby matters so much. That close encounter will be our best opportunity to discover any problem while there is still time to respond comfortably. If Apophis emerges from 2029 on a worrisome orbit, we will still have decades to react. Kinetic impact is not the only strategy. Scientists have proposed several other methods to alter asteroid orbits, each with its own strengths and weaknesses. One is the gravitational tractor, a concept that sounds like science fiction but is grounded in simple physics. A heavy spacecraft would fly to the asteroid and hover near it for months or years. The mutual gravity between the spacecraft and the asteroid would slowly tug the asteroid onto a new path. The process is extremely slow, requiring long-duration operations, but it is also extremely precise and controllable. Another idea is laser ablation. Powerful lasers would heat spots on the asteroid's surface until material vaporizes and escapes as gas. That escaping gas would generate thrust, pushing the asteroid in the opposite direction. It is a rocket engine that uses the asteroid itself as propellant, and yes, there is the nuclear option. Not blowing the asteroid to pieces, that would likely create multiple dangerous fragments, but detonating a nuclear device near its surface. The blast would vaporize a layer of material, generating an enormous impulse that pushes the remaining mass into a new orbit. This is the last resort approach for situations where we need the maximum possible change in velocity with the minimum spacecraft mass. For Apophis, given its size and the long lead times we are likely to have, kinetic deflection would probably be the first choice. It is the technique we have already demonstrated. We understand the physics. We have operational experience from DART, and for an asteroid about 1,115 feet wide, assuming decades of warning, it should be enough. But every deflection mission shares one hard truth. You only get one shot. There is no trial run with a real Earth-threatening asteroid. Either it works the first time, or the consequences play out on a planetary scale. That is why fully characterizing the target asteroid before attempting deflection is absolutely critical. We would need its mass, because that determines how much momentum must be delivered. We would need to understand its internal structure, because that affects how it reacts to impact. We would need detailed maps of its shape and rotation, because those influence where and when to strike for maximum effect. We would need surface property data, because the amount of ejected material controls how strongly the impact amplifies the orbital change. All of that characterization takes time. Likely years of observation and possibly a dedicated reconnaissance mission before any deflection attempt. Enough warning does not just mean enough time to launch an impactor. It means enough time to study the asteroid, design the mission, build the spacecraft, launch it, cruise to the target, execute the deflection, and then observe long enough to confirm that the orbit changed as planned. That full chain could easily span a decade or more, from the initial decision to act to final confirmation of success. Discovering a problem in 2029 leaves room for that. Discovering it in 2045 leaves us scrambling. On top of the technical challenges come political and legal questions. Who has the authority to decide to deflect an asteroid? If Apophis were headed for the Pacific Ocean, would Pacific nations have special input, since a failed deflection might redirect the impact toward someone else's territory? What happens if a deflection attempt fails and worsens the situation? International space law currently offers no detailed playbook. Existing treaties governing outer space were written long before planetary defense became practical. Emerging frameworks, primarily through the United Nations, are beginning to address coordination and information sharing, but clear decision-making structures are still evolving. These are not abstract concerns. If humanity ever faces a real impact threat, such questions will need answers under enormous time pressure and global scrutiny. The more we can rehearse these scenarios in advance, the better prepared we will be in a genuine crisis. Fortunately, Apophis gives us a chance to practice many of these elements without the stress of an actual impact threat. International cooperation on Ramses and Osiris Apex. Coordinated observations by telescopes worldwide. Data sharing among scientists in many countries. All of this builds relationships and establishes procedures we would rely on in an emergency. There is also the challenge of public communication. In a real deflection mission, agencies would need to explain the situation to the world, the risk, the plan, the uncertainties, and the milestones. They would have to update people on progress without inciting panic. They would have to be honest about probabilities while managing expectations. The 2029 flyby, even if it confirms Apophis is harmless, will act as a rehearsal for that communication. Space agencies will brief the public, journalists will cover the story, educators will build lessons around it, scientists will give interviews. All of this builds the communication infrastructure we would need in a real emergency. Finally, there's the question of sustained funding. Planetary defense only works if it is continuous. Nightly telescope surveys are needed to discover new asteroids. Ongoing analysis is needed to refine orbits. Engineers must develop improved deflection technologies. Mission planners must be ready to act when a threat appears. That all requires stable budgets year after year, decade after decade. In a political environment that often rewards short-term thinking, maintaining that long-term commitment is not easy. Here again, Apophis helps. It provides a clear narrative for why planetary defense matters. It anchors the topic to real dates and milestones, such as the 2029 flyby, that keep the issue in public view. Those milestones drive media coverage, public interest, and ultimately political support. When lawmakers see that their constituents care about planetary defense, they are more likely to fund it properly. When space agencies can point to specific events like the Apophis encounter, it becomes easier to justify the budgets required to prepare. So even if Apophis itself never needs to be deflected, the asteroid is already playing a crucial role in developing our planetary defense capabilities. It is a test case, a rallying point, and a constant reminder of why this work matters. Part 8. The Countdown. Vigilance to the very end. So here we are, November 2025. 3 years and 5 months until Apophis makes its historic close pass. Enough time to prepare properly, but not so much that we can afford to grow complacent. What will happen in those next 3 years? In 2025 and 2026, we will see critical funding decisions for Ramses and OSIRIS-APEX. The European Space Agency will need to formally approve Ramses and commit resources. NASA will need to secure continued funding for OSIRIS-APEX's extended operations. Those decisions will determine whether we have eyes on the asteroid during the encounter, or whether we must rely solely on Earth-based observations, looking up from the bottom of the planet's gravity well and trusting our instruments. Through 2026 and 2027, if the missions are approved, the hardware work will ramp up. Ramses will need to be assembled, tested, and readied for launch, piece by piece in clean rooms where a single loose screw can doom years of work. OSIRIS-APEX, already flying through space, will continue its journey toward Apophis, executing trajectory maneuvers and system checks along the way. Its navigation tweaks measured in tiny fractions of a mile per hour, but adding up to millions of miles of displacement over time. At the same time, ground-based telescopes will keep tracking Apophis. Every observation will add data. Every measurement will refine its orbit. Radar observatories will scan it whenever it passes within range. Optical telescopes will capture its position against background stars. Spectrographs will analyze reflected light to characterize its surface composition, turning faint photons into graphs, and graphs into physical insight. All that information will flow into the models. Scientists will use the data to update calculations of exactly where Apophis will be on April 13, 2029. They will refine estimates of the Yarkovsky effect. They will narrow the error bars on mass and rotation. By the time 2028 arrives, we will know Apophis's trajectory with extraordinary precision, far beyond what was imaginable when the asteroid was first discovered. In 2028, if everything proceeds as planned, Ramses will launch. The cruise out to Apophis will take several months, with the spacecraft firing its engines to match the asteroid's speed and slide into formation alongside it. Arrival operations will be delicate, requiring precise navigation and autonomous adjustments as the spacecraft characterizes its target and fine-tunes its own orbit in a celestial dance far from home. Then comes 2029. Early in the year, likely in February or March, Ramses should already be on station, flying around Apophis and sending back the first close-up views of the asteroid from multiple angles. ESA will release those images, and for the first time we will see Apophis not as a star-like point in a telescope, but as a real world with geography, features, fractures, shadows, and personality etched into its surface. OSIRIS-APEX will arrive in April, just in time for the main event. The two spacecraft will coordinate their observations, watching the asteroid from different vantage points as it sweeps past Earth. And then the day will arrive, April 13, 2029. Millions of people will look up. Across Europe, Africa, and Asia, Apophis will be visible to the naked eye, a moving point of light sliding perceptibly against the stars. In dark sky regions far from city lights, it will be fairly bright, reaching magnitude 3, about as bright as the stars in Orion's belt. And people who have never cared about astronomy will feel a small, instinctive chill when they realize that dot is a real object flying just outside the edge of our world. Amateur astronomers will aim telescopes at it. Professional observatories will track it continuously. Radar stations will bombard the asteroid with radio waves, measuring its shape and spin with high precision. Above it all, Ramses and Osiris Apex will watch from the front row, documenting an event never seen before in recorded human history. Closest approach will come around 2146 UTC. Apophis will pass roughly 19,000 to 20,000 miles above the Atlantic Ocean. During those critical hours, Earth's gravity will yank on the asteroid, bending its path by about 28 degrees. Its orbit around the Sun will change from about 323 days to roughly 372 days. It will shift from an Aten-type asteroid, spending most of its time inside Earth's orbit, to an Apollo-type asteroid, whose orbit crosses Earth's but keeps it mostly outside. While all of that unfolds, the spacecraft will measure everything. Exactly how the orbit changes, how the rotation responds, whether the shape deforms, whether dust or gas is released. Every instrument will stream data, filling storage with measurements that will take months to fully analyze. Then, in the days and weeks after the flyby, the real work will begin. Scientists will compare before and after measurements. They will quantify the changes, they will test models against hard data, and they will begin answering the crucial question: did reality match prediction? If it did, if the models held, if Apophis behaved exactly as expected, our confidence in long-term safety projections will soar. We will be able to say, with much greater certainty, that Apophis poses no threat in future encounters. But if there are surprises, if the asteroid changed in ways we did not anticipate, then the calculations will need to be revised. And depending on the nature of those surprises, those revisions could alter the risk picture for future flybys. Either way, we will know. That is the point. The 2029 encounter will turn speculation into knowledge. It will turn theoretical models into validated data. And that, whatever the outcome, will leave us better prepared, not only for Apophis, but for every similar object we discover later. Beyond 2029, the tracking will continue. Apophis will return for another close approach in 2036, though much farther away, about 29 million miles. That distance will be too great for a dramatic show, but close enough to track carefully, especially in light of what we will have learned in 2029. Later encounters will follow in 2051, 2068, 2093, and beyond. Each one will need monitoring. Each will require updated calculations that fold in all the new data. The task of tracking Apophis will stretch across decades, very likely for the rest of our lives and into our children's. And that is as it should be. This is what planetary defense is meant to do: patient vigilance, careful observation, meticulous modeling, year after year, mission after mission, building the knowledge that keeps civilization safe. Apophis is only one asteroid among thousands that require attention, but its size, its orbit, and the timing of its close pass have made it the test case for our entire planetary defense system. If we can handle Apophis correctly, if we can characterize it thoroughly, predict its behavior accurately, and show that our tools and methods work, then we gain confidence that we can manage the next threats, because there will absolutely be next threats. The asteroid belt between Mars and Jupiter holds millions of objects. Orbital resonances and gravitational nudges occasionally send rocks inward toward the inner solar system. Most will burn in the sun or be flung back out into interstellar space. Some, however, will end up on Earth-crossing orbits. We have already discovered thousands of near-Earth asteroids. Survey catalogs grow every year as search telescopes improve. Most are small, capable only of local damage if they hit. Some are larger, capable of regional devastation or worse. And many more almost certainly remain undiscovered. Each new object needs follow-up tracking. Each orbit must be calculated and monitored. and from time to time we will find one that, based on early data, might be on a collision course. Most of those early alarms will fade as more measurements refine the orbit and show a safe miss. But someday, likely in some future century and possibly sooner, we will find one that does not drop off the risk list. We will find an asteroid truly on its way toward us. And when that day comes, all the capabilities we are building now, all the systems we are testing with Apophis, all the experience we are gaining will be the tools humanity uses to respond. That is the real wager. Not just Apophis, not just the 2029 flyby, but the entire long-term planetary defense effort that shields us from one of the very few cosmic disasters we can actually prevent. We are living in the first human generation with the technology to do this. The first generation able to detect hazardous asteroids decades ahead of time. The first able to send spacecraft to study them up close. The first able, if necessary, to nudge them aside. Our ancestors looked up at the night sky and saw the motions of stars and planets as the will of gods. They had no control, no agency, only hope that the heavens would be kind. We know better. We know we inhabit a dynamic solar system where rocks periodically strike planets. We know Earth bears the scars of past impacts. And we know, because we have learned to compute orbits and build spacecraft, that we no longer have to wait helplessly. We can act. We can watch the skies, track potential threats, and take steps to protect ourselves. It is a remarkable achievement, one that quietly hums along in the background of modern civilization. Rarely noticed, yet absolutely essential. But it only works if we keep it running. If we fund the telescopes, support the scientists, launch the missions, build the tools. Planetary defense is not a project we finish and walk away from. It is a standing commitment that must be sustained generation after generation. Apophis reminds us why. In 3 years and 5 months, we will watch an asteroid pass closer than our communication satellites. We will see it with the naked eye. We will observe it with spacecraft. And we will learn from it, adding to our knowledge, improving our capabilities, preparing for whatever the cosmos may send next. The god of chaos is on its way. But this time, we are not frightened peasants praying to ancient deities. We are a technological civilization with the tools to understand, to predict, and, if necessary, to defend ourselves. That does not mean there is no risk. That does not mean there is no uncertainty. But it does mean we have a chance, a real, tangible chance, to protect our planet, our cities, our civilization, from a kind of disaster that no longer has to be inevitable. The countdown has begun. 3 years and 5 months. Let's use them wisely.